Welcome to the Deep Dive. Today, we're plunging to a very specific real-world technical puzzle. We've got a stack of sources here, mostly focused on machine troubleshooting.
Yeah, the core material for this one comes straight from a chat log, actually. It details a specific failure event on a, well, pretty complex machine, and the steps a team took to diagnose and fix it.
Right, and our mission here is basically to extract the critical nuggets of knowledge from this whole technical exchange. We want to understand, what exactly went wrong and really dig into why it happened, see how they addressed it. So hopefully you can gain some real insight into these complex system failures and, maybe more importantly, how to prevent them.
Get ready then, because we're going to unpack the details of a pretty serious machine issue. We're talking melted cables here. And discover the surprisingly simple, probable root cause hiding under all that drama.
Let's jump right in then. The scene opens on, a bit of machine emergency. We're looking at an Okuma LOC650 2SC A1750 machine, serial number 131477 for those keeping track.
And this particular machine had some significant trouble with its spindle MIV.
That's the motor inverter.
Yeah.
Or variable frequency drive.
Exactly, the VFD. And the immediate, undeniable observation right there on the scene was just meltdown cables.
Oof. That's not a good sign.
No, it points directly to a severe electrical problem. Intense heat, uncontrolled, something major going wrong.
So the first big step the team took was naturally pull that drive out. And what did they find right away?
Loose connections.
Ah, okay. So that immediately sparked the big question. Did the loose connections actually cause the burn damage? Or, did the severe damage maybe cause the connections to loosen afterwards?
Right. And the team's strong suspicion, pretty much based on experience with these kinds of failures, was that the loose connections were the starting point. They were the instigator.
Okay, that suspicion sets the stage. Then the sort of structured troubleshooting process really kicked in. An expert came in, not just focused on the immediate fix, but on really understanding the failure.
Yeah, the goal was bigger. To eventually build a troubleshooting guide, maybe even use some AI tools later for diagnostics, all based on what they learned here.
And what's really telling about this approach is how systematic they were, the questions they started asking. They were seeking context beyond just the immediate fault.
Exactly. They wanted to know, was there a maintenance plan in place specifically for checking electrical cabinet connections on these types of machines?
And crucially, if there was a plan, did it specify the correct torque values for those critical bolts? Because that detail, as we'll see, turns out to be incredibly significant.
And how often was the plan followed? What was the frequency?
Right.
Establishing that baseline. They also asked for key technical details, like motor insulation values. You got to rule out a motor fault,
Yes,
right?
actually, yeah.
And the specifics of the MIV and the spindle motor themselves, the machine model, serial number, electrical diagram number, all those pieces you need to build the full picture.
Okay, so when you see melted cables like this on a spindle drive, it kind of begs the question, what are the usual suspects? The common culprits.
Yeah, the expert quickly outlined them, sort of providing a framework for the investigation. Thinking about how spindle drive output cables typically fail like this so dramatically, several common modes come to mind.
Like what?
Well, one is pretty straightforward. Overcurrent or short circuit conditions, just way too much current flowing, maybe from a fault in the motor windings or a problem inside the drive's output stage itself.
Okay.
Faulty components like IGBTs, those are the big power transistors inside the drive, they can fail shorted, basically creates a direct short circuit.
So pure electrical overload from a fault somewhere in the system. Got it. What's another frequent cause?
Then there are loose or corroded connections. This is a big one. It introduces high resistance into the circuit. And when all that current flows through that increased resistance, it generates localized heat right at that bad connection point. This is particularly insidious, maybe, and really common in high vibration environments like, a CNC machine.
So the heat is generated by the resistance itself at the connection, not necessarily like excessive current from an external short somewhere else.
Precisely. It's internal heating at that bottleneck.
Yeah.
Another potential cause is just insulation breakdown. Cables degrade over time. Heat, exposure to oil, mechanical wear.
Sure.
Once that insulation fails, you can get arcing or shorts between conductors, and that generates intense heat too.
And I'd imagine just using the wrong type of cable could cause problems from the start.
Absolutely. Improper cable sizing. If the cables aren't actually rated for the amount of current the motor needs to draw, they'll just overheat. even under normal operating conditions.
Makes sense. And cooling, if the drive overheats.
Definitely. Cooling system failures for the drive itself, or maybe even the spindle motor, can lead to heat buildup inside the whole electrical cabinet. That ambient heat stresses and degrades the cables over time.
Right.
And you also can't forget environmental factors, things like exposure to cutting fluids, oil mist, even metal chips getting in there. They can chemically attack and degrade the cable jackets, making them brittle and prone to failure.
And sometimes, I guess, the drive itself might give you some kind of warning before it gets this bad.
Often, yeah, hopefully. Things like drive faults or alarms on the Okuma control panel. You might see an OL for overload or an OC for overcurrent. Those are designed as early warning signals, indicating a problem before it becomes, catastrophic like this.
Okay, so with this framework of potential causes, shorts, bad connections, bad cables, overheating, environment, how do they actually narrow down in this case? What were the initial diagnostic steps?
Well, the immediate practical step was, frankly, ordering a replacement drive. The source mentions the cost was around $55-90 from Gosiger. Just gives you an idea of the kind of expense involved here.
Yeah, not cheap.
Not at all. They also did a motor insulation check, the Megger test. That's critical to rule out a motor fault causing the issue.
And how did that look?
It came back really good, actually. 550 gigaohms between each lead and ground. So that effectively ruled out a winding fault in the motor as the primary cause of the cable melting. The motor was healthy.
Okay, so motor's good. That points back to the drive or the connection. I saw they even shared some video procedures for testing, emphasizing checking resistance between the U, V, and W output leads on the drive.
Yes, they were trying to isolate the issue specifically to the drive unit, but the definitive confirmation really came from the on-site visit by the Gosiger service rep.
The field service visit.
Exactly. They validated, yes, spindle motor is healthy. And critically confirmed that the spindle drive itself was, completely destroyed, burnt beyond repair. It failed their tests immediately, and they identified the specific unit, an MIV45-3.
Getting the actual photos, and crucially, the machine's error codes from the control panel must have been vital at this point, too.
Oh, absolutely crucial. Requesting pictures, videos of the CNC alarms, the specific drive error codes that gives you the digital breadcrumbs, the trace of the failure event.
And did they find anything significant there?
Yeah, one key alarm they noted early on was 1151 ALARM-A MCS Exception processing. When they cross-referenced that with the Okuma Troubleshooting Guide, it pointed specifically to code #13, which indicates the IPM protective function was activated.
IPM, Intelligent Power Module.
You got it. The core power switching component within the drive itself. So the machine's own alarm history was already pointing towards an internal drive issue related to its main power components, even before they saw the worst of the damage.
Okay, now here's where the picture evidence gets really interesting, right? It tells the visual story. Looking at those photos of the damaged drive, what did they actually reveal?
Oh, yeah. The visual analysis of the pictures was absolutely key to pinpointing the probable cause. Several things jumped out immediately. You saw significant discoloration and soot all around the terminals, especially bad on the U and V phase terminals. That indicates intense heat, maybe even some combustion or electrical arcsing.
Wow.
And you could also see clear signs of melting and pitting on those same terminals. One terminal had that sort of golden flowed look, suggesting metal literally melted and then solidified again. And the pitting. That's classic evidence of sustained electrical arcsing.
So not just like general overheating the whole unit, but really targeted intense heat and arcing right at specific connection points.
Precisely. Localized damage. There was also visible corrosion and oxidation, like a crusty residue built up around the base of the terminals, and that layer is much less conductive than the base metal, which only makes a bad connection even worse, adds more resistance.
Right, compounding the problem.
And of course, the damaged insulation on the cables themselves, it was burnt, cracked, brittle, just destroyed from the extreme temperatures involved.
And all of this visual evidence, taken together, strongly suggested one primary cause.
Yeah, based on those really distinct signs, the localized heat, the melting, the arcing right at the terminals, the probable cause they identified was a high-resistance connection.
And the most common reason for a high-resistance connection on something heavy-duty like this, like what actually causes that high resistance?
By far, the most common reason is just loose terminal bolts. Simple as that sometimes. If they weren't torqued correctly to the manufacturer's spec during installation or maybe during previous maintenance.
Or vibration.
Or, exactly, they vibrated loose over time in the machine's operating environment. If that connection isn't mechanically solid, electrically solid, you get high resistance. Contamination on the surfaces and surface oxidation also definitely contribute by increasing resistance right at those contact points.
Okay, so a loose bolt, maybe some dirt, leads to high resistance. But how does that escalate into, melted cables and a completely burned out drive? That seems like a huge jump from just a loose bolt.
This is where a really critical concept called thermal runaway comes into play. It's a devastating kind of cascading failure mode.
Okay.
You see, a high-resistance connection acts like a bottleneck or like a small electric heater right in the circuit. As all that electrical current flows through it, it generates heat according to that basic physics principle, PIIRR power. Dissipated as heat equals the current squared times the resistance.
Right, the I²R losses.
Exactly. So even a small increase in resistance generates a disproportionate amount of heat because the current term is squared. Now, this initial heat then causes the metal terminals, the bolt, the cable lug, and the surrounding insulation to expand, maybe deform slightly, and oxidize faster. And all of that further increases the resistance at that very connection point.
I see. So the heat itself makes the resistance go up.
Which then generates even more heat because the resistance is higher.
Which makes the resistance go up even more.
Exactly. It's a vicious self-reinforcing cycle. This thermal runaway process just accelerates. It generates escalating amounts of heat until that connection point literally melts, starts arching, maybe catches fire, and causes catastrophic failure of the cables and whatever component it was connected to, in this case, the expensive spindle drive.
Wow. It's actually incredible that something as seemingly simple as a slightly loose bolt through this thermal runaway process can cause such dramatic, expensive destruction. So, okay, what are the big actionable lessons learned here for preventing this specific thing from happening again?
Well, this incident was definitely a stark reminder of the importance of specific, targeted preventative maintenance. The chat log confirms they did actually have an annual PM schedule in place that included checking connections, and it was performed relatively recently, too, back in October 2024.
But clearly, annual wasn't quite sufficient in this case, maybe due to the vibration or workload. Was there discussion about checking more often?
Yes, the idea of more frequent checks, maybe even monthly, was brought up. However, the expert kind of pushed back on that, deeming it potentially excessive and maybe even counterproductive.
How so?
Well, frequently disturbing connections, retorquing them when they might be perfectly stable, can potentially introduce new issues or loosen things that were fine.
Okay. Don't fix what isn't broken, potentially.
Sort of. So a more, let's say, intelligent approach was proposed and agreed upon, basing the connection checks on machine usage, not just the calendar.
Okay, how would that work?
Specifically, performing these checks every 2,000 operating hours using the machine's own embedded hour counter.
That makes a lot of sense. Tying frequency to actual workload and vibration cycles, not just time passing. That's a crucial takeaway.
Exactly. And the sources were very clear on the specific crucial steps recommended to prevent this exact type of high-resistance failure. First, ensure proper torque. Always use a calibrated torque wrench, and tighten those terminal bolts precisely to the manufacturer's specifications, which you'd find in the Okuma maintenance manual.
They mentioned the value they used for the replacement, right?
They did. They noted that during the replacement, they torqued the new connections to 60 foot-pounds, which is about 81 newton meters. Having that specific value is key.
So using the right tool on the right spec is just non-negotiable.
Absolutely critical. Second key step. Thoroughly clean surfaces. Before you make any connection, especially power connections, ensure all the contact surfaces on the terminals, on the cable lugs are impeccably clean. Use an appropriate electrical contact cleaner. Any contamination, grease, oxidation, it's just adding resistance.
Clean surfaces, correct torque based on operating hours. Those sound like the core preventative actions right there.
They really are. And they added another layer of advice, sort of tiered advice, on inspection frequency depending on the machine's operating environment.
Adjusting for conditions.
Right. For standard conditions, reasonably clean environment, maybe single shift operation and annual inspection is probably a good baseline. But this should definitively include thermal imaging.
The heat camera.
Exactly. This was highlighted as probably the most effective, non-invasive early warning tool available for this problem. It lets you literally see the heat signatures from developing high resistance long before there's any visible damage, like discoloration or melting.
So you catch it way earlier.
Way earlier. Visual inspection is still important, of course.
Yeah.
Look for those early signs like slight discoloration. And a manual torque check can be done, but maybe cautiously. Perhaps only every few years, or only if the thermal imaging actually suggests a potential hotspot. Because again, repeatedly torquing might potentially stress the hardware or disturb connections that are perfectly stable.
Okay, so thermal imaging sounds like the key technology here for catching these connection problems before they become, well, meltdowns.
It truly is for this failure mode. Because it detects the root symptom, the heat from resistance, without ever needing to physically touch or potentially disturb stable connections. It's predictive.
And what about for machines that are in tougher conditions? More vibration, running constantly.
Right. For machines operating under harsher conditions, maybe high vibration applications, 247 production, or really high cycle work, environments with extreme temperatures or humidity, or just very dirty or dusty places, or even just older equipment, say 10 plus years old.
Yeah.
For those, semi-annual or even quarterly inspections are recommended for these critical connections. Basically, the higher the stress on the system, the more frequently you need to check it, ideally with that thermal camera.
So the frequency really adapts to the risk profile of the machine and its environment.
Precisely. And just to really hammer it home, the most important takeaway for preventing this specific type of failure, the loose connection leading to thermal runaways, is that annual thermal imaging, at minimum, is probably the single best early warning system you can implement. It's non-invasive and highly effective at spotting these developing high-resistance issues before they cause chaos.
That's a really powerful point. Catch the heat symptom early and do it without potentially introducing a new problem by messing with a good connection.
Exactly that principle.
Yeah.
You verify stability without inducing instability.
So let's wrap up the story then. What was the final resolution for this particular machine, and what immediate actions did they take after getting it fixed?
Well, the good news is the new drive was installed successfully, the machine powered up, and it was turning the spindle just fine. So the immediate crisis was over. The machine was operational again.
Phew. And did they apply the lesson learned right away?
They did. First thing, they checked the temperatures on the newly installed connections, just to make sure everything was running cool and stable after the repair.
Good practice.
And critically, they also made plans to immediately check all the similar drive connections on the other 3 Okuma machines they have on site, applying that preventative knowledge across the whole fleet.
That's a smart move. Proactive prevention on the sister machines before they potentially have the same issue.
Definitely. And beyond just the immediate fix and the fleet check, they also plan to gather the full troubleshooting log from the machine itself, including something called the M-Man history that's from the machine's maintenance interface.
What for?
To look for any previous, maybe subtle alarms or symptoms that might have occurred before the catastrophic failure, could help them refine their diagnostic process, maybe spot trends earlier next time. And they're creating a detailed step-by-step guide specifically for troubleshooting and inspecting this MIV45-3 Brive model for future reference, documenting the learning.
And the final piece was leveraging technology to capture all this, right?
Yeah. The plan mentioned was basically to close out this whole chat thread where all the troubleshooting happened and then feed it into an AI tool to generate a structured, detailed failure analysis report, really consolidating all the information shared during the diagnosis and repair into a formal document.
Okay. So what does this whole deep dive into one specific Okuma spindle drive failure ultimately tell us? I mean, it really underscores that even these incredibly complex, expensive, critical machine components, they can fail due to something as seemingly basic, as fundamental as a loose connection.
It absolutely does. It highlights the immense value of doing detailed, systematic troubleshooting, the power of just transparently sharing observations and data within the team, and maybe above all, the critical importance of implementing very specific, targeted preventative maintenance practices.
Right.
Like using the right torque value with the right tool, meticulously cleaning contact surfaces, and especially the strategic use of more advanced tools like thermal imaging as a powerful early warning system.
Yeah, it's such a vivid illustration of how a truly catastrophic failure melted cables, a completely burned out drive can often be traced all the way back to that initial high resistance connection, just kicking off that destructive thermal runaway cycle.
And the principle here, it really extends far beyond just machine maintenance, doesn't it? It's kind of a lesson about complex systems everywhere. It shows how seemingly small, maybe overlooked details, whether they're physical electrical connections or digital interfaces, or even, communication links within a team or organization, how they can have these cascading, dramatic, and often very expensive consequences if they aren't properly checked, maintained, and secured.
That idea really resonates. It makes you think about those hidden vulnerabilities, the weak links. So maybe here's a provocative thought for you to consider as you go about your day. Where else in your world are there critical connections, maybe physical, maybe digital, perhaps even interpersonal relationships that, if they're left unchecked, unmaintained, could potentially trigger a kind of cascading thermal runaway of problems? Something to think about until the next deep dive.